continue our discussion on the work energy relation. We are going to look at the application of this work energy relation in certain problems. I have mentioned, let me reiterate again, the work energy relation has been derived from the Newton's second law of motion, and this is an integral of the Newton's second law. By integral I mean that it involves a derivative less than a time derivative less than that in Newton's second law. In Newton's second law we have double time derivative, whereas in the work energy relation we have the first time derivative only. So, we have integrated over time once. Let us look at this example of a collar moving on a spiral rod. The problem statement says 0.5 kg collar slides with negligible friction along a fixed spiral rod from A to B. A is this point which is above, vertically above the starting of this spiral. In the vertical plane, this whole rod is in the vertical plane under the action of a constant radial force T is equal to 10 Newton. This should not cause a confusion because this T here is the applied force. The rod shape is described by r theta. I have shown this r, how it is defined as a function of theta and where theta is being measured from. R theta is given by 0.3 times theta, where r is in meter and theta is in radian. Calculate the velocity of the collar when it reaches B. B is on the horizontal plane. If it starts from rest at A, the collar started from rest at A on this spiral path, moves frictionlessly, negligible friction, which means there is no friction in the vertical plane. Therefore, it is under action of this applied force T and gravity. It is under the action of this applied force T of 10 Newton and gravitational acceleration is 9.81 meter per second square. Now, whenever we apply the work energy relation, whenever we represent potential energy, here we have the gravitational field, gravitational force field acting, which is the potential force field, and we know its potential energy expression or the scalar potential function, which is denoted by V. This V, for this V we need to define a datum where V is equal to 0. In this problem I have chosen the datum as this horizontal line. Therefore, this is our datum where V is 0, at this level V is 0. From here I will measure my vertical motion. We have to find out the velocity when the collar reaches point B. The work energy relation tells us that change in the mechanical energy is the work done. Now, here the mechanical energy has both parts, the kinetic and the potential. The kinetic energy part at B plus the potential energy part at B is the net mechanical energy at B minus the net mechanical energy at A. Again it is composed of kinetic and potential energies. Here V is the gravitational potential energy. Therefore, I can easily write the expressions of TB, VB, etc. The kinetic energy at B is half m VB square, VB is not known, therefore, this is the unknown term, plus potential energy at B. Remember that I have chosen V equal to 0 on this horizontal line and B is on that horizontal line. Therefore, potential at B, VB is 0 minus the kinetic energy at A, remember that the collar starts from rest at A, therefore, the kinetic energy is 0, and the potential energy at A. Now, how to calculate the potential energy at A? We know that the gravitational potential energy V is nothing but m g y, and from where y is being measured? Y is being measured from the datum. This is the datum where potential is 0, from there we start measuring the vertical displacement y. The gravitational potential energy which we have derived is m g y, y measured from the datum. Now, how do I find that? M g y, y must be equal to this radial line sin theta. So, this radius, this times sin theta is nothing but the projection on the vertical axis. R times sin theta is the projection of the r the radial distance on the vertical line, because theta is being measured from this horizontal line. Notice that. Now, theta at A, theta at position A is 90 degree. Therefore, this is the expression of y, and this must be at theta is equals to pi by 2, 90 degree. Now, the work done, the right hand side of our work energy relation, it is the work done as the collar moves from A to B. The only non-potential force is that applied force. I have represented that as a vector T dot dr. This is standard definition of work done from A to B. Therefore, I have to now represent these vectors to find out the work done, because it is not a very straightforward path, it is a spiral path. The force vector, force is always acting along the radial line, this is mentioned, it is always acting along the radial line. Therefore, if I choose my E r like this and E theta in the direction of increasing theta. So, this is my E theta 90 degree to E r. So, this is the coordinate system that you can imagine and represent all forces in this coordinate system, forces and displacements. Now, the applied force vector is always along the radial line, which means it is always along E r cap. Therefore, its representation is the magnitude times E r cap. Next, we have to represent dr, the dr vector. For that, let us start with the velocity of this collar. How do you represent velocity in the coordinate system chosen? The velocity is represented as r dot E r cap plus r theta dot E theta cap. I have written this. Now, what is velocity? Velocity is nothing but dr dt, the vector dr dt. That is velocity. I have written this out also for you. dr dt is r dot, the rate of change of the radial distance, which is along E r cap, plus r theta dot is d theta dt along E theta cap direction. This expressions we have seen in kinematics. Therefore, I can remove this dt and hence so let me remove this expression. Therefore, dr must be equal to dr vector must be equal to dr er cap plus r d theta e theta cap. This is the general infinitesimal displacement vector in a polar coordinate system. This is a general displacement vector in a polar coordinate system. Now, we have the applied force vector T and dr vector, then we can proceed. Here r for the problem was given as 0.3 times theta. Therefore, dr which I need here is 0.3 d theta. Finally, we calculate the work done as we move from A to B. Applied force, you can check that this dot product is nothing but T dr, because this is Er and this is Er. Er dot E theta is 0, Er cap dot E theta cap is 0, they are orthogonal. Therefore, only one term survives, this T dr, and dr is 0.3 d theta, which I have substituted here. Therefore, by taking this integral, and this theta starts from pi by 2, it starts from A position which is at pi by 2, theta equal to pi by 2 to theta is equal to pi. When it reaches this position, when the collar reaches position B. Now, it is a straightforward algebra. You have to equate this expression and this expression, which I have done here, and finally, velocity at point B is 5.3 meter per second. So, this is a straightforward. We come to the second problem. A department store escalator handles a steady load of 30 people per minute in elevating them from the first floor to the second floor through a vertical rise of 7 meter. The average person has a mass of 65 kilogram. If the motor that drives the unit delivers 3 kilowatt power, calculate the mechanical efficiency E. This is a problem from the textbook of Merriam and Craig. You have seen such elevators in departmental stores, in at airports, etc. And here there is a tacit assumption that it is constantly delivering people, 30 persons per minute, each weighing 65 kilogram average. We have to find out the mechanical efficiency. How is it defined? It is the rate of work output divided by the power input, and that is what is unknown, and we have to calculate that. Let us look at the work energy relation in the differential form, power form, because here the rate of doing work is specified, and we have to calculate mechanical efficiency, which involves rate of work output and the input power. Therefore, this has to do with power, and therefore, we use the differential form of the work energy relation, which says that the rate of change of the total mechanical energy is equal to the power supplied. Of course, here the power supplied is given to the motor, and the rate of doing work of the escalator has to be calculated, and then there will be a difference. Why this difference? Because there are losses. This is not a conservative system, there are losses. We have to find out how much is the efficiency. Now, if you look at the total mechanical energy E, which is kinetic plus potential energy, then dE dt is d kinetic energy dt plus d potential energy dt. Here we make an assumption that the persons who are using the escalator, they are getting on and off at the running speed of the escalator. Now, why this is of importance? Imagine that you jump on or hop onto an escalator, or just you are standing on the ground and suddenly you place yourself on the escalator almost at 0 velocity. What will the escalator have to do? It will have to accelerate you from that very low velocity or approximately 0 velocity to its steady state velocity. In that, it has to do work. Now, this work is difficult to estimate. So, for the simplicity of this problem, that people do of course ride an escalator, I mean walk onto an escalator at the running speed, and if you have done that, then you will be very comfortable using escalator. If you just place yourself on the escalator with at 0 velocity, you will feel a backward push. There is a toppling effect because your legs are accelerating. Legs have started to accelerate as it has been placed on the escalator, but your body has inertia of rest. Therefore, you have a tendency to topple. Similarly, at the end of the escalator, if you just stand there, if you just get off the escalator and try to be at 0 velocity, you will have a feeling of going forward, I mean falling forward. Therefore, you assume in this problem that the rate of change of kinetic energy is 0. People are getting on and off the escalator at the running speed of the escalator. The escalator does not have to accelerate or decelerate a person. In that case, the rate of change of total mechanical energy is nothing but the rate of change of potential energy of the system. Now, the potential energy is nothing but mgh. How can it change? M normally is a constant, g is a constant, h is traversing, it is taking these people up by 7 meter, fixed height. Therefore, what is the rate of change of potential energy? That has to come from m dot, because this is not a fixed mass system. This system is not a fixed mass system, mass is coming in and going out, and because of that there is a mass influx and efflux, and for that the dV dt, that means rate of change of potential energy, is m dot, rate at which people are being transported to this height h, rate at which people are being transported to this height h is m dot g h. Therefore, we have to calculate m dot. How do we calculate m dot? Persons per minute using the escalator is 30 given. Therefore, per second, persons per second is persons per minute by 60, and a person weighs 65 kg per person on an average. Therefore, kg per second, which is the mass transport rate, it is the number of persons per minute by 60 into 65, which is 30 by 60 into 65, that happens to be 32.5 kilogram per second. This is the rate at which mass is being transported to this height of 7 meter. So, therefore, the rate of work output of the escalator, mechanical work output of the escalator, which is dE dt, is 32.5 kilogram per second m dot into g into h, and that turns out to be 2.232 kilowatt. But the motor is supplying 3 kilowatt mentioned in the problem. Therefore, I can calculate the mechanical efficiency, which turns out to be 0.744. Where what is happening to the rest of the power? It is getting lost in dissipation, friction. Next we look at this problem of a flexible chain like a bicycle chain. A flexible bicycle chain of length pi r by 2. So, it is a quarter of this circle which has been shown, circular path, and mass per unit length rho is released from rest on in a smooth circular guide with theta equal to 0. You can note here how theta is defined. Theta is defined to the end of the chain from this vertical. Calculate the velocity of the chain when theta is equal to pi by 2. When theta is equal to pi by 2, what happens to the chain? It has come out of this circular slot and it is now falling under gravity, it has become vertical. This is a problem of the book of Merriam and Craig. We apply the work energy relation. The change of mechanical energy is equal to the work done as it moves from A to B. Now, position A is when theta equal to 0 and position B is when theta equal to pi by 2. We have to calculate the velocity of the chain when theta equal to pi by 2 in position B. Let us look at this figure that I have drawn when the chain has become vertical, that means at theta equal to pi by 2. Now, this is in a uniform gravitational field, the whole system is in a uniform gravitational field, the thing is in a vertical plane. Therefore, the chain is driven by gravity. We have to calculate the gravitational potential energy of the chain. For that, we look at first, let us look at the total mechanical energy. The change in the total mechanical energy is the total mechanical energy at B minus the total mechanical energy at A, which I have written out. Here the potential is due to gravity, and that is the only force which does the work. There is a normal reaction from the circular guide, but because it is frictionless, remember this guide is frictionless. Therefore, this normal reaction is the only force of interaction between the chain and the guide, and normal force is perpendicular to the direction of motion of the chain. And you must recall, we have discussed this, that work is done only by the tangential component, not by the normal component. Therefore, this normal component will not do any work, it is out of the purview of the work energy relation. Had there been friction, then that would have come through friction, because friction acts tangent to the path, and then the problem gets more complicated. Anyway, our problem is frictionless. Now, we have to calculate the kinetic energy and potential energies at these two locations. The work done as the chain moves from position A, the configuration A to configuration B, there are no other forces than the potential force, which is gravitational force, and that is already included in V. Therefore, other than this there is no other force. Therefore, work done by any other external force is 0. Whatever force comes is a potential force, and that has been included in V. Now, we try to calculate the kinetic and potential energies at the two configurations A and B. At B, which is this vertical configuration which I have drawn here, the kinetic energy is, imagine you have a short length of this chain as ds, represented by ds, then rho times ds, rho is the mass per unit length, and therefore, rho times ds is nothing but the mass of this little element which I have marked out. Mass of the little element, half of mass of little element times velocity square. This is the kinetic energy of this little element, and if I integrate this expression from 0 to L, that will give me the total kinetic energy of the chain. And if you do this calculation, then it is half of rho pi r by 2 v square. Here this integrand has no dependence on S. Therefore, its ds integrated from 0 to L is L, which is length of the chain. Therefore, this is my kinetic energy at position B. Potential energy at position B. Again, imagine this little element which is at the depth d minus S from the 0 datum. I have taken datum as this vertical, as this horizontal line as the datum where V is 0, and to calculate potential energy of this little element which I have shaded, I have to look at the displacement from the datum, and mgy as you know. So, rho times ds is the mass of that little element g, and the distance from the displacement from the datum, which is minus s. Therefore, the potential energy of this little element is rho g minus rho g s ds, and when you do this integral straightforward, you will get this as the potential energy expression. Okay, we have the kinetic energy and potential energy expressions at B. Now, we have to calculate the potential energy expression at A. Kinetic energy is 0 because the chain starts from rest at A when theta equal to 0, but the potential energy expression is requires a step. Again, imagine this element. Here I have marked out this element ds. This ds can be written as radius times d theta, and d theta is marked here. I have to calculate the potential energy of this little element. First, rho is the mass per unit length, r d theta is the length. Therefore, this is the mass, rho times r d theta is the small mass of the element, g, and height of this element from the datum. Now, height from the datum is this. This is nothing but radius times cosine theta, radius times cosine theta, and that comes here as height. And if you do a calculation, this is the potential energy at configuration A. Now, it is a straightforward application of the work energy relation. Work done from A to B is 0, and therefore, on the left hand side we have T B plus V B minus V A equal to 0, from where you can calculate the velocity of the chain, and this is straightforward algebra. I will leave it to you. Finally, we come to this problem of a boy of mass m is standing initially at rest relative to a moving walkway. This is a walkway, again you will find such walkways in airports where you have long distances to cover. There are walkways like this. This problem says, therefore, this boy of mass m is standing initially at rest relative to a moving walkway which has a constant horizontal speed u. He decides to accelerate his progress and starts to walk from point A with a steadily increasing speed and reaches point B with a speed x dot equal to v relative to the walkway. Here you should note that A and B are being fixed points for a ground fixed observer. So, I as a ground fixed observer or you as a ground fixed observer, you are observing this boy, and at A he decides to accelerate and reaches B with a velocity which is now relative to the walkway equal to V. During his acceleration, he generates an average horizontal force F between his shoes and the walkway. Write the work energy equation for his absolute and relative motions and explain the meaning of the term MUV. This is again a problem from the book of Merriam and Craig. This is a very interesting problem and a very educative problem for understanding work energy relation in a moving frame and a fixed frame. Now, the work energy relation is of this form. The change in the total mechanical energy is equal to the work done. There is no change in potential energy in this case. Let us first look from the eyes of a fixed observer, an observer who is fixed to the ground and watching this boy. For that observer, the velocity of the boy is velocity of the walkway plus the velocity of the boy with respect to the walkway. This is plain relative velocity concept in a non-rotating frame. Velocity of the walkway is u, which is constant, and x dot, it is marked there in the figure. X dot is the velocity of the boy relative to the walkway. Therefore, for a fixed ground fixed observer, the velocity of the boy is u plus x dot. Okay. The kinetic energy of the boy at B minus kinetic energy of the boy at A must be equal to the work done as the boy moves from A to B. I can write down the kinetic energy at B, which is half mass of the boy times the velocity of the boy at B, which is u plus v, which comes from this relative velocity expression. U plus v is the velocity of the boy as he reaches B. Therefore, half m u plus v whole square minus kinetic energy of the boy at A, he was standing there. At A, he was standing, he just started to accelerate from A. Therefore, the kinetic energy of the boy at A must be half m u square, which is the walkway velocity, and that must be equal to the work done by all the forces acting on the boy as he moves from A to B. Now, as a fixed observer, suppose what I will see, this S is the distance, as I mentioned, A and B are points fixed in the ground fixed frame. Therefore, x is S, this S which has been marked is the distance travelled, net distance travelled between A and B, and whatever be the force that is acting between the boy and the shoe, boy's shoe and the walkway, it is F, and F dot S is the net work done on the boy, which changes his kinetic energy as given on the left. If you simplify, then you get half m v square plus m u v is equals to F times S. Now, let us switch our point of view for an observer I call A, who is fixed to the walkway. Now, this observer A is fixed to the walkway. For that observer, the velocity of the boy is x dot, because when the boy was standing, for that observer, the boy has no velocity, no relative velocity to that observer's frame. By the way, both these frames, the ground fixed and the walkway fixed frames, both the frames are inertial frames. One is fixed with respect to distant stars, the other is moving at a constant velocity to this fixed frame. Therefore, both are inertial frames. Now, again I can write the work energy relation as written by this observer A. Observer A is sitting on the walkway and noting down, writing this work and energy relation. What does this observer observe? The velocity at B, when the boy has reached this destination B, the velocity is half m v square, v is the relative velocity, minus initial kinetic energy is 0. So, final kinetic energy is half m v square minus initial kinetic energy is 0 is equals to F times S prime. Now, what is this S prime? Force is the same, force on the boy's shoe is the same, whether it is measured by the ground fixed observer or the walkway fixed observer, but the distance travelled is different. Distance travelled on the walkway is different from that which is observed by the ground fixed observer. This you can very easily understand. And if you do this calculation, you get half mv square is equals to f times s prime. Now, what is the difference? F s minus s prime is equals to m u v. This is the term which has been asked in the question. What is this term? Where from does it come? To understand this, let us look at the free body diagram of the boy as he accelerates on the walkway. Since his acceleration is a force equal to mass times acceleration must be acting from the walkway onto the boy, and the direction of the force is shown because the acceleration is towards the right. Therefore, the force must be towards the right. Now, let us try to calculate the time required to accelerate. Final velocity is v is equals to initial velocity is 0 plus acceleration into time of acceleration, which means the time of acceleration must be equal to v by a. Now, work done by the walkway, let us try to calculate the work done by the walkway on the boy. F is the force that is acting between the walkway and the shoe of the boy, and this is the only force in the horizontal direction, and this must be doing the work. This work must be F times the distance travelled by the boy, distance travelled by the walkway in that time, because this force is acting between the boy and the walkway. This force acts for that much time as long as the boy is accelerating. Now, this same force is acting on the walkway also. Therefore, the work done by the walkway motor is this force times the displacement of the walkway during the time of acceleration, and displacement of the walkway is u. U is the velocity of the walkway times the accelerating time of the boy. Therefore, F dot u times T A velocity into time is the distance covered by the walkway during the acceleration time, and the force acting is constant, and u times time of acceleration is v by a. Therefore, this is m u v. This is the work done by the walkway on the boy. Therefore, the net work done by the boy, the work done by the boy has to be measured on the walkway frame, because the boy is walking on the walkway, he is accelerating, he is using his energy to accelerate only the distance he is covering on the walkway. Therefore, the work done by the boy must be F s prime plus the work done by the walkway on the boy is m u v. This is the total work done as observed by the inertial observer. This is the total work done as measured or as calculated by the inertial observer. Therefore, inertial observer sees everything in the system. Inertial observer can see the work done by the boy and the work done by the walkway in accelerating. When the boy is accelerating, the walkway is doing work, it is maintaining its velocity. Therefore, it must be applying additional torque to keep its velocity constant, because boy is taking reaction from the walkway. This force F is taken by the boy from the walkway, and the walkway is still moving at a constant speed. Therefore, the walkway motor must be doing that extra work, and inertial observer observes everything. To summarize, we have looked at the application of the work energy form of the Newton's second law. This, let me reiterate again, is an integral of the Newton's second law and leads us to the conservation of energy, and we have understood the application of the work energy relation through certain problems. With that, I will close this lecture.